Hi guys.
Hello.
Well,
Hello.
I thought a little water music for a environmental modeling class would be appropriate. Handel's. How many of you have heard of Handel's water music before? Nobody's even writing it in the chat. Wow. So I introduced something new to you guys today. Handel's water music. I like it. It's actually good. He did it actually because there were these boats that went out on the rivers, and they would take a small orchestra out with them to play for the people that were on the boat. So that's why they called it the water music. Um, okay, we've got 65 people. Shruti, you there?
Hello, Dr. Jeffrey.
Uh,
Can you hear me?
yeah, I like that. Club can't handle them. You can't handle. Okay. So how'd it go on Monday?
It was good. There were at least 25 to 30 students who showed up. So
Okay.
I think
So
I also received almost all the submissions now. Almost.
okay, good. So I will give that homework was over rivers, right?
Yes.
So we've given one over lakes, we've given one over rivers, and now I owe you guys homework over groundwater. So I'll give you a groundwater assignment this week sometime. So look on Brightspace. Before Friday, I'll post homework. I'll probably give you this weekend and next weekend to do it. So I'll be doing about a week and a half again. Um, so you don't have to rush. But I think I will have finished everything today. So there's a few final sort of clarification things on groundwater. I've got some slides of one of my projects that had to do with groundwater that I'm going to show you. But let me first, I got to share this. I'm going to share my screen. So we're up to over 70 people, so most people are here today. In the groundwater N13C document, PDF, we went over this idea of how many pore volumes were pumped at 24 sites. This is an old table, but the idea is some of these sites, for example, this IBM site in San Jose, these are contaminated groundwater sites, and some of them are quite large. And some of them pump out, like this one, 23,000 liters per minute, which is 23 cubic meters per minute, which is a lot of water. But then the area is 310 hectares. So some of these sites are large groundwater contamination sites. And this is years to pump 24 volumes. So that's what we said last time, that most of these, a lot of the groundwater sites, it's a matter of retaining the contaminants on the site or under the site and not letting them run through the ground or in the groundwater off the site. So the groundwater is moving off the site, but we'll put in cutoff walls and everything else to so that we don't get water going off. So on the same document then, on this page, which is page 9 of 10, treatment of pumped water methods. So there's in situ treatment. Whenever you hear the word in situ, it means on site. So there's on site, and really it means in place treatment. In other words, you don't dig up the groundwater, you treat it in site. So you do injection wells and put chemicals down to do some oxidation or reduction reaction. A common one is zero valent iron for for chlorocarbons. So you can put a cutoff wall in that is porous but has zero valent iron in, and then as the plume of contamination is coming through, the chemicals are reduced and dechlorinated, so that what's coming out on the other side is less chlorinated, or sometimes totally unchlorinated compounds. Not always, but at least that way, when you reduce the number of chlorines on the molecules, then the microorganisms may be able to actually finish the compounds off by oxidative processes. So heavily chlorinated PCBs, for example, only undergo reduction reactions, whereas ones that only have 1 or 2 chlorines on can actually be metabolized by microorganisms and be oxidized. So air stripping is one way. And we've talked about Henry's law, so you know, hey, if I'm putting air through water and that those air bubbles are saturated with the chemical that's in the water by the time that the air bubble gets up to the top and breaks, you could actually calculate how much air you have to put through something to basically strip out all of the contaminants, assuming that you have equilibrium partitioning to the gas bubble by the time the bubble reaches the surface. So the finer the gas bubble, the more distribution to the bubble you're going to have, or the more saturated the bubble is going to have, because it's a surface area to volume phenomena. So air stripping, you can actually air strip in the vadose zone. So oftentimes I think down here we have something. Well, no, I don't. But you can put a sparging tube down in the unsaturated zone and basically blow the contaminants out and then capture them as they're coming out of the surface. Capturing as they're coming out of the surface is problematic, but you can also pump the other way, where you're pumping it out through the pipe and then treating it at the end of the pipe. Adsorption, desorption, carbon. There are actually a lot of places that do this. They use activated carbon as an adsorbent. Activated carbon has a high surface area. Chemicals absorb to it. Usually you model it with a simple Freundlich isotherm. But if you've got a water plume that is contaminated with some contaminants and you don't have a whole lot of other organic matter in the water, you can absorb those contaminants, and then you have to deal with the activated carbon. So it's carbon disposal. You can actually take it to an incinerator and burn it, or you could potentially wash off the carbon and reuse it. Steam stripping. Now you have to treat the condensate. You strip with steam, and then as the steam condenses to form water, you have contaminated water. Chemical oxidation. For a while, people were putting permanganate in the subsurface to oxidize chemicals. You can put ozone in the subsurface to oxidize chemicals. Biodegradation. How can you augment it? By adding maybe some additional carbon sources that are easy for microorganisms to break down, just so that you have a higher population of microorganisms in the subsurface, so that now that higher population potentially can break down other contaminants that are in the subsurface. So you modify it. It's almost like fertilizing your lawn. Hey, you want your grass to grow better, you put fertilizer on. Well, you want the bacteria to grow up, you give them a little bit of extra food, and then they're around to break down the other contaminants that may be there at a low concentration. Membrane filtration. This is often used actually to remove solid particles from groundwater, because even in the subsurface, you've got lots of fine particles, and those fine particles, colloids, have a lot of contaminants on them. So before you dispose the water, which could be low in contamination, you remove the fine particles by membrane filtration, and it basically cuts down on the amount of contamination that you're that's in the water, and then you may be able to discharge the water to the sanitary sewer and have the city treat the rest of the water. Obviously, you need a permit to do that, but you could. They may even say, we don't want any particles. You have to remove the particles with a membrane filter, and then we'll take the water that's coming through that filter in the sanitary sewer. Precipitation, sometimes you can do this with metals. Sometimes you can put in a cutoff wall that will precipitate heavy metals. So if you have a plume of contamination and it contains some metals like copper or cadmium or lead, chromium, you may be able to put in a cutoff wall that contains a co-ion that can precipitate that out, or just absorb to it. And the common thing here is, again, putting in zero valent iron, because zero valent iron oxidizes slowly. As it oxidizes, then other metal species absorb to it. So things like even sulfates, you can precipitate metals with now with sulfides. Sulfides are very famous as ways of precipitating metals, because iron sulfide is not very soluble, but mercury sulfide, copper sulfide are even less soluble. So if I put in iron sulfide into a system, I'm going to replace some of the iron with some mercury or cadmium or copper or other things, because they're less soluble than the iron. Ion exchange, then you have water to dispose of. In 360, we do an ion exchange experiment where we put copper on an ion exchange resin, kick off the sodium ions. So you could do the same thing if you've got metals in a plume. Maybe you've got chromium-3 in a plume. Well, you could run it through an ion exchange resin, capture all of the chromium, exchange it with sodium, and then you have to deal with the backwash water, which is high in chromium. But then you may be able to precipitate that chromium out and reuse it, send it back to the factory where the chromium originated, and they can reprocess it. Reverse osmosis. This is generally done to really clean up the water. So reverse osmosis is used in drinking water. It's rarely used in water contamination or groundwater contamination issues unless you're going to drink the water. So reverse osmosis removes the organics, it removes the metal species, it removes just about everything. The only thing it doesn't remove is the water. So on NPR today, they were talking about the nuclear reactor in Japan that has all of this contaminated water because of the tsunami that hit a few years ago. I don't know if you guys remember this. Unmute yourself and tell me if you remember about the tsunami in
I do.
I can't spell tsunami. Here's video of the tsunami. Tsunami is basically a tidal wave. It's when an earthquake happens in the ocean.
All across northern Japan.
And here you go.
The largest.
Look at the water coming in.
The magnitude of the March 11th disaster. It was the largest quake ever known in Japan.
This is 2011. Look at it, it's moving buildings.
People are confirmed dead or missing. When two tectonic plates, waves enter shallow.
They go through this whole thing.
Japan may be the GPS station.
Come on, where is it?
The river at Hitatsunaka, and can perhaps help us better understand the power of earthquakes and tsunamis and prevent loss of life in the future. Moving as fast as 5 miles per second.
That's fast.
In this photo, the ripples of tsunami waves are seen moving upstream in the Naka River at Hitatsunaka City. New
Look at
technology
this.
left
I mean, I would hate to be in that water.
for study in years to come. It can perhaps help us better understand the power of earthquakes and tsunamis.
But anyway, it knocked out a nuclear power plant that was right on the coast. And as a result, they have all of this contaminated water that are in tanks, and now they're dealing with it. Water waste. Let me see if I can find it. Yep, this is it. NPR. Japan to dump wastewater from wrecked nuclear plant into the Pacific Ocean. So there's a lot of protests going on about doing this, but they've treated the water apparently with something like reverse osmosis. They haven't said exactly, I don't think. But because a lot of the water radioactive is hydrogen isotopes, hydrogen is, a half part of water, H2O. And so if you get tritium contamination, obviously reverse osmosis isn't going to take out the tritium. So they remove the uranium and the other heavy isotopes because those are ions that stay on one side of the membrane. But obviously it's still contaminated with a lot of radioactive water, basically. The tritium only has a half-life of about 7 years. So, yep, tritium here. The nonprofit health, tritium is going to be hazardous. It is because it's basically radioactive hydrogen. But you get the idea. There's we've talked about two nuclear disasters. One, it's not necessarily a disaster that it's like it happened immediately. It was something that happened over about a 40-year period in the state of Washington with the Hanford site and its contamination, which is hugely polluted. And then this nuclear treatment facility too, having to deal with water. So we're still not there on how we deal with energy. But anyway, reverse osmosis can be used. And in that case, I think that's what they did use to remove the uranium and other things. But the problem still is the heavy water still gets through because it's moving through with the water, obviously. So they basically concentrated the really bad nuclear isotopes, but not the tritium, not the protons that are basically have two. Tritium is basically a hydrogen atom with two additional neutrons in the nucleus. So it's got an atomic mass of 3 rather than regular hydrogen, which is usually 1. And there is some. Let me look up one other thing. I know I'm getting off of things here. Hydrogen, here's hydrogen. Okay, so it's got an atomic mass of 1.008. Over here is chlorine. Chlorine is atomic mass of 35.45. Why is hydrogen not 1? Why is carbon 12.011? I thought they did carbon as 12. What's this 0.011? You have to unmute yourself because I can't see the comments. I can't see the chat. Isotopes, yeah, exactly. So carbon has a little bit of C13 naturally occurring. It doesn't have much C14 naturally occurring. It's got some, but not very much. So the average weight of all carbon on Earth is 12.03. It's interesting because chlorine is one of the few where it's almost halfway in between. There's 2 common isotopes of chlorine. One is 35, and I think the other is not 36, it's actually 37. And both of those are stable isotopes because the number of neutrons in the nucleus. So over here, hydrogen, there's a little bit of deuterium, which has a proton and a neutron in the nucleus, obviously. But tritium, hey, it's very, very rare, and it's basically we get it from bombarding things with other atoms and stuff, and it also forms from the decomposition of uranium and other heavy radionuclides. So it's obviously a problem in nuclear waste. So you get the idea. Even the atomic mass of these are because of the different isotopes of these elements. But chlorine is the biggest problem. If any of you do any mass spec analysis, chlorine containing compounds are really, really difficult to look at because of these different weights. Because you're basically, what a mass spec does is it looks at the mass of the molecule. Well, if you have 2 or 3 chlorines on, that means for the same compound, you're going to have 5 or 6 peaks because they're all going to appear at the different atomic weights of the chlorine, of the individual molecules. So mass spec is where you can really, really see that difference. So ion exchange, reverse osmosis. We don't do a lab on reverse osmosis, but reverse osmosis is pretty straightforward. Basically, but we talk about it. We've talked about it in this class, where you're basically pressurizing water, pushing it through a semi-porous membrane where the water goes through, but because of the properties of the membrane does not allow ions to move through it. So reverse osmosis is a good way of deionizing the water too. It also doesn't allow large macromolecules to go through, like humic acids, fulvic acids. So you remove all of the organic matter from the water. A few small organic molecules may get through, but not very many. Like ethane, ethanol might come through, things like that. But it's mostly water, and then the ions, just because the membrane is fairly hydrophobic, it doesn't allow ions to dissolve in the membrane like it does for the water to dissolve in the membrane. Then oil-water separation, this is one of the most common things, because if you have a groundwater that's contaminated with a non-aqueous phase liquid, a NAPL, and that NAPL can be an L-NAPL or a D-NAPL, either a light non-aqueous phase liquid that floats on top of the water, or a D-NAPL, which sinks into the water and it becomes very, very problematic. So oil can be heavy oil, it can be light oil. But once if it's a light oil, if you pump out the water, the first thing you do is put it in a big tank. The oil floats on top, and then you can skim that oil off and drain the tank from the bottom, and then with the permit, potentially dispose of that water through the sanitary sewer. So that way you keep the oil, and then the oil may go to a hazardous waste landfill, or it may be incinerated, depending upon what kind of oil there is. So disposal of the oil, incineration, or some other process. So here's an example. Here's transport contaminants to extraction oil. I've got, this is below ground, this is above ground. I turned it sort of sideways, so I'm on a steep slope here, but think of this as being sort of a flat slope. That we are pumping water out at this well, and then we may be doing pH adjustment. We go through an oil-water separator. The oil goes to the incinerator. We have transportation costs to get it there. The water then goes through an activated carbon absorption unit to remove organics that are not removed by a separate phase process. Then we have fairly clean water, but then the activated carbon, we have to dispose of it, or we can regenerate it with heat. And then, so we could heat it up, and then the off gases we have to do something to. We could maybe UV treat the off gases, or do something else with the off gases to basically break down the organic chemicals, or even just heat them up to the point that they're incinerated, that they're basically all oxidized. The clean water then is we can re-inject it for hydraulic containment. So we contain our plume of contaminants here on site by re-injecting our clean water after we've basically cleaned it all up, and then basically it's pushing the contaminated water towards this pump, because we're increasing the groundwater table here, we're decreasing the groundwater table here, because we're adding water here, we're taking water away here, so the water flows from this point to this point. The clean water, we could go through aeration or some other processes too. But you get the idea. Is environmental engineers, we deal with systems. We don't just pump the water. It's not just one system that we're dealing with. We're always doing multiple things. Each of these is a separate process, and we're linking processes together in a treatment train. So it's being the water's first being treated here to remove the major contamination from it. Then we're removing more contamination here. Then the clean water may be being aerated again to basically induce some microorganisms or something before we re-inject it. So we're doing treatment processes one after the other, and how we sequence these are very important. We don't want to send our water through a carbon absorption, because then all of the oil is going to get stuck to our carbon, and we're going to have a real mess. So the sequence of treatment technologies is really important. If you take a wastewater treatment course, it's the same way. You go through a initial water clarifier to settle out solids, and then the water goes to an activated sludge plant to remove the dissolved solids or the dissolved organic material by biologically consuming that material into biomass, into microorganisms, and then you settle out the microorganisms and you end up with the clean water. So you're going through a series of treatment processes to basically end up with clean water in the end. And you have to do it in series, and each of those processes has to work efficiently to do it, okay? So you're designing a whole system to treat things. And there's costs associated with each of these. So just like you guys take a life cycle analysis course, well, life cycle is sort of the same thing. Only now you're looking at a product that you make, and how do you break, where does it go? It gets used, and then how do you break it down? And part of it goes here, part of it goes here, part of it goes here. You know, you got a whole stream of processes to treat all of those different materials, whether it's a car with plastic and tires and metal, you know, and oil and other things. You're doing a whole treatment process, a treatment train, okay? So that's the end of these slides, but for water, these are some of the processes that we use to treat the water. And some of these are big processes like biodegradation. Each different organism has different enzymatic systems, and some compounds can be broken down easily, and some compounds cannot be broken down easily. These are old notes. Nyes used to work a lot on biodegradation. Right now, George Zhao is doing a lot of, most of the biological work. Chemical oxidation, I know Swaz done a lot of work on chemical oxidation processes. and so is Amisha Shaw. And then over here, there's, lots of other processes, but you get the idea. Some of these are degradation type processes where the compound is mineralized to CO2 and water, oxidation and biodegradation type processes. Others just simply remove the contaminants, or like adsorption or steam stripping. They're phase transfer processes. It's going from a water phase to a gas phase, or it's going from a water phase to a solid phase. So these processes, like adsorption and steam stripping, are phase, or even air stripping. These are phase transfer. We're transferring the chemicals from one phase to another phase, solid, liquid, or gas. Whereas these processes are mineralizing the compounds generally. Chemical oxidation may not oxidize it completely to CO2 and water, but it may oxidize it partially so that microorganisms can start chewing it up and mineralizing it completely. Membrane filtration, this is a phase separation process, but it's not really phase separation, it's just concentration, because everything stays on one side of the membrane or the other. It stays in the water phase, but you're concentrating it. And then this precipitation is a chemical. It is a phase transfer process in a way, because the ions are going from the water phase, dissolved in water, to becoming a solid precipitate, a salt. When you precipitate out metals, you're forming a salt. You're forming an iron sulfide, or calcium carbonate, or whatever that salt is. Solid phase. This is a phase transfer because it's going from the aqueous phase onto the solid phase. So you guys get the idea. We have different processes, and they don't all look alike, and the fundamentals of each one are completely different. But to treat groundwater or to treat surface water, those are the kinds of things that you do. Here we go. Here's our landfill. Here's our river. And this landfill has a clay layer underneath it that is 0.3 meters thick. So it's a thin layer here. And our landfill, of course, we sited right above the water table, right? We didn't put it in the water table. So here's our aquifer. This is a glacial till aquifer. And in Indiana, we have lots of glacial till. If you look at Indiana, let me see if I can dig up a map of Indiana. I'll just use Google Maps. Why not, right? I don't need a fancy map. I'll just use a Google map. I could maybe do, here's Indiana. And let's do the satellite. Look at this. What happened here? Why is this so flat? Anybody know? Why is northern Indiana so flat, southern Indiana is not?
Because of the glaciers flattened out, and by the time it got to southern Indiana, it was melting out and turning into glacial outwash.
Yeah, I'm going to try and find it. If the last major, the Wisconsin glaciation extended from approximately 75,000 to 11,000 years ago. Okay, this is called the Wisconsin glaciation. And let's see if we can find an image that shows where it extended from. They don't have, here we go. This shows you where the glacier, pro-glaciation lakes of the Great Lakes Formation and all of this stuff. You can find maps of this stuff. It shows you where the glaciers were. But 11,000 years ago, that's actually kind of amazing that we had glaciers in Indiana 11,000 years ago. It was fairly recent. So we have in Indiana all of this glacial till because the glaciers move things, they move rocks and everything else. We have clay layers below Indiana, and then fractured limestone, bedrock, and other things. But if you dig down, we have in Indiana, we have about 15 feet of topsoil, and then we've got glacial till underneath that. Sometimes this clay comes all the way up to here, and we don't have glacial till under everything. The topsoil is basically right on top of the clay, and in that case, the water pools on this, and we don't get good runoff because we don't have a glacial till for the water to move through. But this is it's called glacial till because it got deposited by the last glacier period. The height here, I'm just saying 30 meters. Over here, 29.5 meters for the water table height. This is relative to sea level, even though I'm assuming that this is completely flat. But this 30 and this 29.9 is relative to the same point in elevation. 60 meters from this point to this point. So we've got two places for the water to flow. The water has to flow through the clay lining of the landfill. It hits the water table, and then it's flowing in the groundwater to the river. So we've got two things impeding a contaminant in the landfill from reaching this river. We've got the clay layer underneath, and then we've got the flow of the groundwater in the glacial till aquifer. This, again, this little symbol here indicates that this is a water level. This is a soil level. And our landfill is here. We put a well in here, and H3 is equal to H1 minus 1.8. I don't even know what that means. What does that mean? But the height there is 0.3 and 0.1. So I think this means what? I'm not sure. We'll figure it out. So what is the vertical velocity of water through the clay seal? How long will it take the water to percolate through the clay? And then how long will it take the leachate water to reach the river once it is broken through the clay? And what is the vertical component of the velocity vector? How long will it take to reach the bedrock? In other words, the water is still actually going down here. Oh, that's what I did. H3 is equal to H1 minus 1.5. That means that this level, we got water going in here. Is that right? What is the vertical component of the velocity vector? How long will it take to reach the bedrock aquifer? You have water flowing in this direction too. That's what I mean, is the water level here is such that this is a confining layer, but you also have some water flowing through here. But that means that we need to know the thickness of this layer. Our confining layer is 3 meters thick. Our confining layer is 3 meters thick. I give you a porosity and I give you a hydraulic conductivity. So you can actually calculate, knowing that this is 30 meters and the difference between H1 and I think this is H3 is 1.8 meters, the water pressure across there. So that means that I can calculate the flow of water in this vertical direction. I can also calculate, because I know the difference in height there and height there, I can calculate the water flow in this direction. So in actuality, the water, once it hits the water table right here, it's flowing with a vector this way. It's flowing mostly in the vertical direction, but because there is some flow through this confining layer, it's flowing down, which, hey, that's why I have this slope here too, right? Okay. So To go through these calculations, answers to the questions, just use Darcy's law. I know what K is, so for doing this clay liner in the landfill, I know the hydraulic conductivity is 0.4 liters per meter squared per day. Again, I could actually calculate this in a velocity because liters is also, I could convert that to cubic meters, right? Cubic meters per square meter gives me meters. That's meters per day. So this hydraulic conductivity is like a velocity in a way. But I can also write it in these units of cubic length per squared length per time. So I just use these values. I know it's 12 centimeters thick. I know there's 0.3 meters at the bottom of the liner, so I can actually use that as my hydraulic gradient. So I have 0.3 over 12. This is my delta H over delta L. Conversion factor times hydraulic conductivity gives me that many meters per day. This is how fast the water is moving through my clay layer. This is the specific discharge though. Okay, to calculate the actual velocity, I have to divide by n to get the actual velocity through it. Since I know it's going through 0.12 meters, that's the thickness of my layer here, right? Since that's the thickness of my layer, 0.02 meters, again, most of these problems are just looking at the units. This is the velocity, it's going this distance. Distance divided by velocity gives me time. It takes 54 days for the water at the bottom of this aquifer, right on the bottom of the clay, not aquifer, landfill. Right at the bottom, right at the top of the clay, it takes 54 days for the water right there to reach the bottom of my clay layer. And then I got a little bit of vadose zone here, but basically from that point on, it's in this aquifer. So it takes 54 days to go through my short little clay layer, okay? Assumption, I'm assuming that delta H is constant. So as it's going through, I'm assuming that the water is being replaced on top. Then 2, I do the same thing, only now I'm doing it with this. I got 30 meters of head here, 29.5 meters of head here. I'm going over 60 meters of distance. I know what my K value here is. It's much higher because now I'm in an aquifer. So my hydraulic conductivity in clay is really, really low. My hydraulic conductivity in a clay and in a sand, and this is clay down here. I should say sand and gravel here, okay? My sand and gravel aquifer is like huge, 4,000. So minus 4,000 times my delta H is 0.6 or 0.5. That's my difference in height. And then 60 meters is my distance, my delta L. Unit conversion again, it gives me my specific discharge. My actual velocity is this, and that means it takes about 2 years to reach the river. So 54 days, but 2 years. It's kind of amazing, but it's because this is a long distance. Its travel time is about 2 years to get to the river. So it comes through in 54 days, 2 years to reach the river in that way. And then the last problem is independent of V vertical in the confining layer above the bedrock. My delta H is 0.8. That's my delta L is 3 meters. So this thickness is 3 meters. My delta H between the bottom here and the top is 1.8 meters. So I'm telling you that it's 1.8. The pressure difference at this point and this point, okay? The pressure distance here is actually this 30 meters, but then that means that at this layer below it, it's 1.8, which means it's actually slightly less. If it was slightly more, it would actually be, the water would actually be flowing up. If this was an artesian well, in other words, and my pressure was up here, my water would be seeping up through here and then running to the river. But I got a lower pressure down here than up here. So I'm not experiencing all 30 meters of pressure down here. It's actually lower. So my water is running through this. So if I go through the same calculation here, and now I put in my n so that I can calculate my actual velocity directly. This is my actual velocity because I'm dividing by n. I could come up with 13,000 days or 37 years. And that's because this is such a huge confining layer. I've got 3 feet rather than 0.3 feet of clay. And and in this case, actually this is lower than this. I've given this a little bit higher value, but it's got a lot longer distance to travel through because the K and the difference in K here and the difference in what in distance, 3 meters versus 0.3 meters. Or no, this one's only 12 centimeters, whereas this one's 3 meters. Okay, you guys get the idea. Just plug and chug is the answer. This is the actual velocity. Then I've got 30 meters plus 3 over this. Tells me that I'm adding the 3 because I've got 30 meters. So I'm calculating how long it takes to go through it, but I'm not calculating it from this point to this point like I did in my clay layer. I'm actually calculating it from this point up here. It's got to go 30 meters plus it's got to go another 3 meters. So that's a part of the calculation because it's moving very, very slowly through here. That means it's also moving downward here at the same rate, very, very slowly. So I'm calculating the whole distance from this 30 meters plus this 3 meters to get, that's what part of the reason why it takes so long, 37 years to go that whole distance. Okay? You guys get the idea. You could do the same thing and add biodegradation as a reaction to this. Because if I had biodegradation, I could actually calculate, if I know the travel time from here to here, and I know the first order decay constant, I could calculate how much of my chemical, if I'm coming in at a certain concentration here, well, what's my concentration coming out here? Because I know the time it takes to get from here to here, assuming this is like a plug flow system, right? And we've talked about plug flow systems. You know what those are. You just assume that you don't have dispersion occurring. And in this case, it would be a reasonable assumption because we're just doing a back of the envelope calculation to calculate what would be my concentration coming out at this point if my chemical is moving in this direction. Okay? Any questions? I think I'm going to, I guess I could leave this up if you want to unmute yourself and ask me any questions. I will give you some problems similar to this to do because it's basically we've done 2 things here. We've used Darcy's law, but the other thing that we've done also is on top of Darcy's law, we've calculated retardation factors, which basically tells you how fast the chemical is moving relative to the water. Okay? So I'll give you some Darcy law problems and also some retardation calculation problems to look at. Any comments or questions? Nobody's. So you know what you're looking at right now? Somebody guess.
Your view.
Yeah, that's outside my window. Here I am. That's outside my window right now. It's pretty nice. It's a nice spring day, so don't stay in all day long. Get out there and play a little bit. Okay? It's an order. I'll see you on Friday, and by then I'll have the next homework posted. Okay?
Thank you, Dr. Alfred.
Yeah.
Have a good day.
Good day.
Yeah.